Okay, welcome to the last week basically of instruction. Next week is reserved basically for testing. From the get-go, I'm going to change the format for the last exam to a different one. It's going to be basically, you will be given the review hopefully by Thursday, if not Friday. Okay, you will have the review. The review will be graded as participation, meaning that you're strongly urged to take it. Whatever you get in it, it doesn't matter. If you start it, you're going to get full credit for it. Okay? So, in other words, I strongly urge you to do the review for the exam. And then it's going to be basically multiple choice. It's going to have about between 250 to 300 questions. That is the review, not the exam. Okay? Where you're going to go and start it. It doesn't matter how much you score in it, you're going to get full credit for the review, which is going to go towards your participation grade. Okay. Then the exam will be available on Thursday, December 10th, starting from in the morning. I really didn't decide yet, but most likely it's going to be in I'm sorry, we usually do it in the evening for this class, so I'm confusing with another class. So we're going to start around 4 o'clock and end it sometime in the evening to give you time. If you're working during the daytime, you can come still at night and complete your exam and we'll be done with it. So it's going to be graded by Canvas. So hopefully you guys, if you complete the review perfectly, you should not have any difficulty taking this exam and you'll be done with it and we'll be done completely, okay? In terms of also participation, this discussion today is going to be graded. The one on this coming Thursday is not going to be graded, okay? I will be available for Tuesday next week. There will be no lecture. The only thing I will be available for if you guys have any questions or difficulty with the review or anything like that. So that's basically in preparation for the final, for the last exam of this class, okay? So this is in a nutshell what we have going right now. In terms of this class, some of you who are sitting in Physics 11, there is something similar going on for Physics 11. First of all, you should have received an email today regarding the submission for your for those working on the motor. For those who chose to make the report, you're going to get also the instruction for it this Thursday, and then you're going to submit it also by next week. Okay, but you still have an exam coming next week, okay, for those who are not doing the motor. Okay, if you are not sitting in Physics 11, ignore what I was talking about. If you are seeing Physics 11, you know exactly what I'm talking about. So because a lot of my Physics 11 students happen to be in my Physics 10 class, so that's why I'm making this general announcements for what everything is. Okay, so let's talk about the class today. And why is it blank? Okay. Whoa, that's not what I meant. Stop sharing. Show more windows. Okay, this is the one I meant to share. Okay, so this you should have had in your in the class, okay, part of the normal stuff that they usually publish, including the summary of the chapter. So in these two chapters, actually, it's basically they're interconnected. It's nuclear physics, both because radioactivity is also nuclear physics. So that's basically what we're discussing today, okay? The discovery of the X-ray radiation toward the end of the 19th century, around 1895 by Röntgen. And then later on was basically the studies that Marie Curie have conducted in the past with her husband, basically, because initially it was both her and her husband. And then after he passed away, she continued the work. I know the discussions in the beginning was about some of the classes, at least. I think some of you again are sitting in Physics 11 and you know that topic. Is about the Nobel Prize winner from different kind of minorities, and a lot of you chose her name. So again, she was a woman basically who. Let me give her a little bit of credit because she's one of the pioneers in science. She's an exception in a lot of ways, okay? She was a leading scientist in a field that she basically discovered on her own, radioactivity, okay? She's actually the one who gave her that name to this field of science. She discovered some elements. One of them is polonium, of course, and polonium is the reason why it was called polonium is because she is Polish originally. She was from Poland, so that she honored her native country, and then also she did a lot of work for her adoptive country, namely France. So because she spent most of her life later on when she married Pierre Curie. So that's basically something that she did. And also there is something that at least in the discussions in the beginning, some of you missed, and I'm hoping that you guys will pick it up in the discussion today. So the topic today is about Marie Curie, okay? So I want you really to dig more on her and basically learn more about her. One of the things that she did actually do, and it's an exception, she's the scientist who won 2 Nobel Prizes in 2 different branches of science. She had a Nobel Prize in physics, and then she earned a different Nobel Prize in chemistry. So that's really something that somebody who is a scientist who has 2 different Nobel Prizes in 2 different fields, and she was a woman, of course. That's also another thing that you have to recognize, and the fact that women were not really supposed to be. I mean, at least there is a lot of bias against women at that time. So she overcome a lot of basically adversity, and she became famous. And one of the things that she did, and I really want you to mention that also, is the fact that she sacrificed her life literally, because she exposed her entire life working basically with her hands on radiation. And now people believe, actually, because at that time there was no research based on the effects of radioactivity, that she died because of exposure to highly radioactive materials that she was working with. The other element that she discovered also is radium. She's the one who actually gave him that name because of the radioactivity, the phenomenon itself. So she did a lot of things in science. She was an inspiration, at least for myself, when I was growing up in middle school, learning a lot about her and how much she did. And she was really inspired me a lot to really pursue stuff in science. And I'm hoping that some of you will at least honor that fact, the fact that she did so many things, and she accomplished so much in her life. And I'm hoping that people who have adversity in their lives, doesn't matter whether perceived or real, they need to really pick up some of these things that, hey, if that person can do it, why can't I do it? And that's really the thing that needs to be there. The other thing also is policies really need to change. And to recognize the fact that diversity is really critical to the advancement of science in general, because if the 2 of us sit together and piggyback on each other, we will basically we will exhaust all of our ideas, and we cannot really advance in science. But if we bring somebody else who have different experience and different perspective on things, we may have a different view on something that we've been looking at it only from a single angle. Now we have a different perspective on it, and we could move on. And this is true whether it's physics, whether it's astronomy, or this research that's being conducted right now on coronavirus. So these are some of the things that I really want you to pick up from this thing. And this is the topic of the day, namely radioactivity that she discovered. So that's the topic number 1 for discussion, okay? Reflect on Marie, I don't know if she spells it with the English way or the French way, Curie, I think it's like this. Life. She spells it with the French way. Okay? So that's really the topic of the topic number 1 of the day. Did everybody follow? Yes, no, maybe? Good? Okay, very good. I'm glad that people are on board now. Thank you. So the topics again of the day are the X-ray radiation, radioactivity. There are 3 types, and for those sitting in Physics 11, they know about this one because it was part of a lab activity. 3 types of radiation: alpha, beta, and gamma. They're the first Greek letters, alpha, beta, gamma. So alpha are the so-called, basically they are the ionized hydrogen particles. They are heavy, they have big mass. They also have big charge. They have 2 electronic charge, 2 charges of the electron, and usually they are positive because of the fact that you have a helium atom stripped of its electrons, so you have just the ions. And then beta radiation, typically it's just a negative version of it, which is an electron basically escaping very fast. There is a different kind of beta radiation that we don't really, initially at least we didn't see it in the laboratories, and that involves actually something called positron, which is an electron with a positive charge. Of course, that's short-lived. It doesn't live too long because the minute it meets another electron, they annihilate one another and they go poof and they go away. Okay, they go actually in bursts of energy, which is actually kind of another radiation, which is a gamma radiation. When gamma radiation was discovered, it was a puzzle. It's very similar to the X-ray actually, because X-ray radiation was unique in a sense that when Röntgen actually discovered it, he discovered that it's very powerful. It penetrates the skin, it penetrates solids, and it's going to be observed after, depending on the thickness of the material. Lead is a good absorber for it. That's why you see people who deal with radiation to have lead around them, because it absorbs X-ray radiation. And depending on the thickness, of course, of the material. The problem with it is, of course, is that it doesn't deflect in the magnetic field. And like the alpha particles or the beta radiation, they both deflect. Alpha particle deflect one way. The beta radiation deflects in the opposite way because they have opposite charges, okay? And then gamma radiation and X-ray radiation, they go straight out, okay? X-rays, they go straight out because they don't have a charge. They're actually a regular electromagnetic radiation, okay? Just like light, basically, except they happen to be too energetic. The difference between the two is light involves transition of the upper electrons. Ultraviolet, a little bit lower electrons. X-ray radiation involves a transition of the innermost electrons. So they go up. So there's tremendous amount of energy when they go back in. Okay, and they emit that much energy, tremendous energy, high frequency, very short wavelength, and they could be damaging, as I said before. Gamma rays, they don't involve any electrons, they involve actually the nucleus itself. So they are extremely short, highly, much higher than the X-ray radiation in terms of frequency and energy. So that's basically the difference. But all of them, they are electromagnetic waves, just not too far from what light is, except light is a lot less energetic, much longer wavelength than these things, okay? We talk about environmental radiation. This is one of the things that people talk a lot, especially when they talk about pollutions and things like that, and realize that actually what you think is probably maybe dangerous is not really that dangerous compared to where you are seated right now. You are bombarded by the radiation coming from the cosmos, coming from the outside of your house, coming from outside of the Earth completely. Okay, cosmic radiation is very, very, very dominant in where we live, far more than what we produce. That's one thing. The other thing also, the earth and the ground and the material that makes up the place where you live also is highly radioactive, much more radioactive than your cell phone, for example, which emits actually radio waves, which is really harmless compared to what we're talking about, okay? We're going to talk about the atomic nucleus and the strong nuclear force. Again, we're doing nuclear physics. Nuclear physics is, again, the forces of nature. There are 4 of them. Okay. Gravity, which is the weakest of them all, followed by electromagnetism, which is a lot stronger than gravity by a factor of 1, followed by 39 to 40 zeros, basically. You cannot even say this number. It's too big. It's not a billion. It's not a billion of a billion. It's more than that, okay? So electromagnetic radiation, which is electric fields, electricity, and all of the things, and what holds us together and everything. And then you have 2 kinds of nuclear forces. The first one is the so-called strong nuclear force, which is stronger than even the electromagnetic radiation. And then there is one responsible for radioactivity called the weak nuclear force, which is actually weaker than even the EM waves, electromagnetic force, but it's much stronger than gravity. Gravity is really nothing compared to all of them, okay? If you have had a chance to look at the book by Stephen Hawking on the history of the universe, basically, it's a good book, and it talks about these 4 forces and how they split in the initial blink of an eye, or less than a blink of an eye, from the initial time when the universe was formed, basically from the Big Bang. And he talks about how these 4 forces used to be only one force. We don't know how gravity broke out of the 3, but it broke up early, and then followed by the electromagnetic radiation, and weak force from the nuclear. So the nuclear separated from the other two, and finally the other two split among one another. And this whole thing took less than a billionth of a second from when the Big Bang happened. Okay, so it's so rapid. So it's a fun book to read. It's a good book to read. When I talk about radioactive life, half-life, that's something that characterizes all materials that are radioactive. Radioactive materials are usually heavy materials. They have a large mass, but some low mass materials also can become radioactive, and they are. Like, for example, carbon-14 is radioactive. Some isotopes from low mass elements, they are radioactive. Radiation detectors, transmutation of elements, they change from one material to another just basically by doing this radioactive materials. This was one of the dreams of the alchemists in the old days, trying to make gold out of iron. Well, you cannot really make it with chemistry, but you can make it with nuclear physics. All you have to do is just basically change the nucleus enough to get the material. The problem with this operation, it's not really cost effective. Costs you more to produce gold than the actual gold you end up with. But it is doable using transmutation, okay? And then arithmetic dating is used basically to date materials, whether they are organic or non-organic. Organic materials, usually they use carbon-14 again when it changes to nitrogen, and then it has a half-life of about 5,700 years. So you measure if the material, the animal or the object was alive during its life, so it produces a certain amount of carbon-14. You go and measure today and find the ratio of carbon-14 to carbon-12, and you will see, based on that ratio, how old. When was this material alive? Okay, so use that. That's for carbon dating. It's also used for it's called carbon dating for living organisms, but it's radiometric dating for anything else. For example, for rocks. Again, you use different elements in this case, for example, that have very long, like uranium, for example, or potassium that has very, very long life, half-life. So you use that instead to date those rocks. You know, for the early on, how much, for example, you're supposed to have from the parents and how much you have now from the daughter, and based on the half-life, you're going to deduce the life. How long was it when this rock basically formed, or when this object was formed from the time on. So that's how we actually came up with the age of the Earth and a lot of the stuff that we come up with for about 4.5 billion years. Nobody was alive then to date or give the birth of the Earth when it was. So that's what we use again for these things. Okay. Then we're going to delve into the second part of this chapter, this class, which is nuclear fission. Okay. And this was one of the advancements that happened in the 20th century. Okay, once we discovered the new force, the nuclear force, exactly. This is part of the history that I really want you to also remember. Once we discovered chemistry, okay, and we played with chemistry, what we ended up with is actually making and understand it. We were doing the powder, and we were building guns, okay, and then basically bombs using chemistry, and those are powerful stuff. So with the mastery of a force, and that force actually is electromagnetic force in this case, that's exactly what it is for chemistry. Once we mastered that force, we built bombs. And those bombs were very powerful compared to the previous ages. So the civilization that controlled that made those gunpowders, was really far more powerful than the ones that could not master it. Then we mastered the strong force, the strong nuclear force. So what we did was a nuclear bomb, which was compared to the powder, compared to the gun that we used to use, is a huge advancement in technology. The civilization, or the country that controlled it, basically was far more powerful. Of course, the United States used it twice. Okay. And it's tremendous energy that made it. Of course, we did not necessarily, I mean, it was war that funded it initially. and then it ended World War II. Some people argue that was actually a good thing. Otherwise, the war could have devastated more people, and so that there is some pluses and minuses to these things. And now we're talking about actually another thing that is going on, and that is the superstring theory and things like that. So the speculation is the following: if somehow a technology or a civilization can control that, the new kind of physics that is outgoing out there, that is, people are working on it, superstring. So imagine what you can do, because basically you can tunnel, you can destroy this whole universe, you can create your own universe, you can do the things that you can do is probably endless. That's why there is a race there actually trying to master that technology, and the people who master it first, probably they will have tremendous powers in their hands. So this is what happened in the past. This is exactly what this chapter is talking about. What could happen in the future is another story, okay? So again, that is, we're going to talk about it into how it was basically used in reactors. That's actually applications in the industry. And there is a lot of politics, of course, involved with it. Unfortunately, there is more fiction to it than science. Nuclear fission is no more dangerous than carbon-based, basically, reactors, okay? Than fuel, for example, using. So it's really not much difference in that. And that's one thing. Then there is also another thing that fission actually produces, because initially it needed uranium-235. Uranium-235 is a rare element in the ore when you go and collect uranium. There is 99.3% of the ore is actually uranium-238, which is really useless. 0.7% of it is the uranium-235. So initially you really have to enrich the uranium to bring it to the more active one, the one that is really useful, which is uranium-235. So that's really the biggest problem that you have to overcome. But then what happened was, uranium-238, because of its presence next to uranium-35 that is reacting, because of the escaping neutrons, it's going to capture neutrons and becomes uranium, becomes actually a different element. Uranium-239 first, then a different element. What is it? Neptunium-239. But this is really not a stable element. It has a very short half-life, about 14 days. Then that one actually by itself changes into a different element called plutonium-239. So plutonium-239 is actually as good as uranium-235. So this reaction by itself can produce for you more fuel than it consumes. Isn't this nice? Can you think about this? You go to the gas station. It reminds me of another thing. You go to a gas station and you pump, for example, 5 cents, or let's say, for example, 50 cents of gasoline, okay? And you pour in it another, for example, 10 gallons of water, pure water, in your car, and you drive. Your car will consume the 50 cents of gasoline or half a gallon of gasoline that you put in the car, but then also changes the water into gasoline. Isn't this nice? It would be nice if we can make this technology in real life. The gasoline, wish, yeah, it would be nice. But that's exactly what these breeder reactors are. They produce more fuel than they actually consume because of this process. Because again, uranium-238 is so much abundant versus uranium-235, which is very, very little of it. So uranium-235, through this process, through this two-step process, will become uranium-238 becomes plutonium-239. And plutonium-239 is as good as uranium-235, except the problem with it, it's highly radioactive. And one of the issues, at least technological issues, on how to dispose of it, because there is abundance of it. It's being made continuously, a lot of it. So how can you get rid of it? Is right now, the easiest solution is to dig very, very deep in the earth and basically bury it there. So that's really one of the solutions that we have in there. Until we run out of fuel, then we're going to go and dig it up and put it in the reactors again and use it as fuel, because it can be used as fuel or bombs or whatever you want to make. Okay. So again, this is the power. It's all based on this famous equation by Mr. and how basically, in order to understand it and what's going on in here in this case is, you have a heavy element, which is really an unstable element. The reason why it's unstable is because there is a competition of two forces, the nuclear force and the electromagnetic force. The electromagnetic force, you have two protons next to one another. They don't like to be next to one another, so they repel one another. But the nuclear force, actually two protons will attract because of nuclear force. To help them stay together, neutrons come in and help them stay together. But as the atom grows bigger and bigger and bigger and bigger, the protons from the other end will be too far away to impact one another due to the strong nuclear force. So the only thing that remains in that stage is the repulsion due to Coulomb's force. So in this case, when the atom becomes, the nucleus becomes too big, then it becomes unstable because of this imbalance between the two forces. Okay. Now so it splits. Once it splits, and you add up the masses of the things that split. Usually, it splits in different elements. You have two different elements. You add up their masses, and you add up the masses of the escaping neutrons or whatever other particles that come from it. You will find that there is an imbalance in terms of the mass. There is mass lost. And that mass that is lost is the energy, because of the famous equation of Mr. Einstein, E equals to mc squared. So whatever loss is in m multiplied by the speed of light squared, that is the energy that escapes. Okay, tremendous energy that is going to be generated. Okay. You follow this process. As the element becomes less and less, this process is less and less energy efficient until you reach iron. Iron, you cannot split it to make out of it energy. It costs you more to split iron to get energy. You cannot get energy from it. You have to put energy into it. So in other words, that nuclear reaction is not an exothermic reaction, it's an endothermic reaction. You look at the same graph from the opposite direction. Elements that are light, you can combine them, and the combined mass is less than the initial mass. The initial mass is much higher when they are separate. For example, an isotope of hydrogen called deuterium and another isotope of hydrogen called tritium. You put them together, and now you end up with a new element, which is helium plus or lithium plus other stuff in it. You add up the masses, you will find that they are less than the initial masses you start with. The missing mass again is energy, E equal to mc squared. And this is true when you're combining elements. You'll get more exothermic reactions than, so you'll get more energy, but it's going to be less and less efficient again until you hit the bottom of iron. Once you're in iron, you cannot do anything. You cannot do anything with iron. You cannot combine iron with another element or with the iron itself to make up more energy. That is not possible. You cannot split iron to find a higher energy. No. Once you reach iron, you have reached rock bottom. You cannot do anything with it. This is actually the process that is going on in all the stars, the ones that are going through a normal life. The big enough stars, like our sun, it's not going to reach that stage. But other stars, they're going to go in producing nuclear reactions inside their core, making heavier and heavier elements, and they're happy about it, and they're good. The minute they make iron, a star would have signed its own death. It cannot continue anymore. It's going to collapse on itself and basically go into either a neutron star or become a black hole. So it's really the end of the everything for a star. So star is happy to make any element up to iron. After that, it's not going to be able to. So you're asking and wondering how in the world then we get other elements higher than iron. Well, the star can go supernova, and when it goes supernova, during that stage, there is enough energy, although it's not efficient, but it can make other heavier elements, the gold and whatever other elements that you have in the periodic table. So that is how the process works. Okay. So this is there is a graph that we're going to get into at the end to understand why the ratio of the mass to binding energy is critical in here, and to understand why iron is really the death. So coming fission, you're coming from one side to the curve. Fusion, you're coming from the other side of your problem. The only difficulty we're running in right now is controlling the fusion. Fission, we can control it. We can make nuclear reactors with it. You have rods that have the fuel in them, and you have rods that slow down the neutrons that are emitted from the nuclear reaction. So if you push them in, they can kill completely the nuclear reaction. It stops at once. Or you pull them up. As you pull them up, there are more and more neutrons, so the nuclear reaction increases higher and higher and higher, and the reactor can go actually critical and can explode if you're not careful enough. So those are the controlling rods that basically control the nuclear reaction. They usually are made of different elements that observe initially it was used graphite, but other elements also can be used to slow down the neutrons that are escaping from the nuclear reactions that just happened. So you can control the fission. Fusion, it's very hard to control. So at this point, it's one of the top research. There are two techniques that are known, whether you use magnets, super strong magnets, to like the tokamak, basically the nuclear reactors that the Russians started, is trying to tokamak was, I don't know, anyway, so trying to confine, because they are supercharged, highly charged particles, and when you try to bring them closer together so that they fuse, they don't like to come together, so they repel one another. So you use super strong magnets to try to bring them closer and closer, and if you do, they will fuse. Right now, this process is not efficient. It costs you more energy to get them closer than the energy you get out of them, because you're not bringing enough material together. Okay. Another process uses actually lasers. So you have laser beams shooting and pointing in the same direction, and laser beams exert pressure also. So what you do in this case, you drop pallets of hydrogen pallets, and as they fall between those lasers, they are ionized, and then they are close from one another, so they fuse. But that too is not energy efficient. The energy you get from it is a lot less than the energy you put in it. So at this point, the technology is not really fully mastered. But if it's mastered, we have the #1 element in the universe, namely hydrogen, that we can use as fuel. And this is limitless in terms of amount of energy that you can have, far more than uranium-235 for fission. So if we can somehow, if civilization can control this thing, they will have abundance of energy. It will cost you nothing to make anything basically work. But at this point, it's very, very difficult to do it. There is no process, at least the only one that we know of that occurs naturally is inside the stars. And that's how the process is working inside the stars, basically, that stars is fueling itself. And because tremendous pressure coming from gravity, that supplies that confinement. So even though, and it's hot enough, so the temperature is hot enough that they are ionized, but the hydrogen atoms, they have nowhere to go because of this tremendous pressure, so they fuse. Okay, that's how what's going on, at least in nature. We don't have any other process for it to make it, at least in real life. So that's the 2 chapters for you guys. Any questions? Okay, so let's get into a little bit of details in here. Okay, again, this is Röntgen and how he discovered the X-rays. Okay, the X-rays, yes. Okay, the X-rays, as I mentioned before, the reason why they're used for X-ray radiation, for example, when you go and have your hand examined or check a broken bone or something like that, is because of the fact they penetrate materials straight through and through, and you can make the dosage in such a way that they reflect just from solid surfaces, and you have an image of the inside of it. Okay, so they have the property of not deflecting in their magnetic fields, and they are highly energetic. Okay, and they're actually produced by ionization, actually, of the lower innermost orbitals of the electrons, as I mentioned before. This is the image that you can obtain from it. Okay, if you're worried, I mean, I know the technician, the first thing he does is he runs away when you are inside the room. Don't worry too much, because actually you're receiving more radiation somewhere else too. Because it's the exposure is usually short-lived. Okay, when he or she presses the button, usually it clicks just a certain very high dose of radiation, but over a very short span of time. So it's not really that dangerous. Of course, the reason why he or she runs away is because of the fact that they're doing this day in, day out. So they don't want to be exposed too long for it. Okay. So radioactivity, as I mentioned before, was actually it was discovered by Marie Curie with her husband before he died in an accident, actually. Okay, and is the process of nuclear decay. That's because materials change from one form to the other in the decay. Nothing new in there. It's been going on since. This is true. This is, I mean, some of the misconceptions are actually, and some of the political groups, they think that this is something has to do with the industrialization. No, it existed before. And as a matter of fact, the only reason why we exist on Earth is because of it. The reason why the core of the Earth is so hot and molten is because of the radioactivity occurring in its core. And it's the Earth core. So it's molten because of the radioactive materials. For example, if you take Mars did not have a lot of materials in it to begin with compared to the Earth and Venus, so therefore most of its heat is basically dissipated, and whatever current it had before is not enough. Otherwise it spins as fast as the Earth. So if it has a molten rock like the Earth, it should have a strong magnetic field, and it doesn't. The strong magnetic field is really what protects Earth from the cosmic radiation and solar winds that could cause the end of life very quickly. Okay. So within minutes, actually, life will end if we did not have that magnetic field. Okay, so that's really why it's a natural process. So that's what it is. So it's not Marie Curie that made it. So it existed before that. Okay. So the radioactivity occurs in the soil we walk on, in the air we breathe, interior of the Earth. So it's all of the above. Okay, again, there are three types of radiation. Alpha particles will deflect in one way, and that, as I mentioned before, they are the ions of the helium. They're the helium nucleus. Basically, it has two charges because it has two protons in it and two neutrons. And then you have the beta decay. Beta decay, actually, there are two kinds, as I mentioned before. There is a beta negative, and there is a very short-lived beta positive. This, we discovered it in the chambers, basically, in cloud chambers in nuclear reactors, nuclear accelerators, and there is a different one that immediately combines with electrons to go to basically gamma rays. Gamma rays are not deflected, meaning they don't carry charge with them, and they actually don't carry mass with them, and they're just normal electromagnetic radiation. This they carry mass, this they carry mass, this they carry charge, this they carry charge, and this charge is twice as much as this one, and this has none. It's only pure energy, basically. Okay. Again, depending on the material itself, the penetration can depend, first of all, from material to material, and also from the thickness of the material. Radioactive alpha particles can be stopped with paper. Beta particles can be stopped by thin matter like aluminum. And gamma radiation, because they don't have mass, they don't have charge, so you really need a very thick medium like this one to stop them, okay? Lead to stop them, because they're going to go straight through, not deflected with the charges, not reflected with charges, not interacting with mass, because they don't have none of that. But again, they can be absorbed by the nucleus of a certain materials if they're given enough depth. So they go, they don't interact, they don't miss this atom, they don't miss this atom. I don't mean the atom, I mean the nucleus. So they miss this nucleus, they miss this nucleus because they came to this way or that way. But then ultimately they will go head on with the nucleus of some sort if the material is thick enough, and that's when they get observed. And that's why you're going to have it, you're protected with it. So that's the difference between them, okay? These ones are supermassive alpha particles that they're going to ultimately, because they have a big charge, even if you have a thin one, they're going to hit because they're big, so they have a big cross section. So basically, it's like taking a basketball, for example, and trying to throw it against the screen, for example, of your window. It's going to bounce back. That's basically what alpha particles are. They're big, massive, so when you throw it against the screen, it's not going to go through the screen. Whereas, for example, the beta particles are a lot smaller, okay? A lot smaller. So think of the same screen, but now you have to have actually double layers of screen if you have tiny particles trying to go throw them through it. So it's not a basketball anymore. And alpha particles are even, you need much, much bigger space in that one because they can go through the screen quickly, okay? So the origins of the radioactivity goes back to, no, the military activity in 20th century, that's true. It's not when they built the nuclear bomb. And the Industrial Revolution 2 centuries ago, no. The beginning of the human era, no. It's way before humans basically walked on the earth. That's what radioactivity is. Any atom that emits an alpha particle or beta particle becomes an atom of a different element always. So, if you have an element, can I draw it here? Yeah. If you have an element, it has, for example, I don't know, let's say, for example, 20 protons, okay, and plus some neutrons, and emits an alpha particle. Now, you have moved from 20 protons to about 18 protons, and whatever number of neutrons, now it's also moved by -2. So this entire element, the new element, is a different chemical element in the periodic table, completely different than the first one. Same thing, if the same 20 particles instead gave you a beta particle is a negative electron. So that means that this proton has been promoted to 1 more in order to keep the charge the same. So actually this moved in the opposite direction. Okay, this moved to the left, and this moves to the right in the periodic table. This element is higher in the periodic table than the previous one. This element is lower in the periodic table, comes before the first one in the periodic table. So an element goes radioactive alpha particle by moving back in the periodic table. An element goes radioactive with beta decay by going actually forward, 1 step only forward. This one goes 2 steps backward, and in here it goes only 1 step forward for this process. So you end up with a new element, okay? It's not an isotope. Isotope is the same element, same protons, but different neutrons. No, okay? So it's not an isotope, okay? Increases its mass? No. It actually decreases the mass because you lost 4 nucleons, okay? May become an atom of a different element. No, it's going to become an atom of a different element, always. So the correct answer is A. Man, time is flying and we're barely in. Okay, treatment using radioactivity is actually good to kill the germs in it. Okay, so some materials there, some produced produced, for example, is exposed to radioactivity, for example, alpha particles, to kill whatever living organisms in it. But then, depending on how you tune it, then this material actually now is devoid of any radioactivity after you do that, so it's safe. Again, radon is a hazardous material that is, first of all, this is the sources of the different kinds of radiation that we have. The vast majority of it is coming from cosmic radiation in Earth itself and radon in the air. So this is a natural process. 75%, 3/4 of the radiation that we have is naturally occurring. Some of it is coming from medicine, for example, and diagnostics like X-rays and things like that. Some of it is coming from food, 8% from food, naturally occurring food, not something that goes through a process or anything like that. And then nuclear plants represents less than very, very tiny fraction. And then other consumer products, about 2%. Radon is something that seeps, especially in the basements, and you have to be very careful with it. and it can accumulate over time because basements usually have very little ventilation. So you really have to be careful with it because it could build up and is actually highly radioactive and can cause problems. So usually there is a way to treat it and test for it. And if you have it, you have to make sure that the place is safe. Okay. Radiation is measured in RAD, okay, radioactive decay or whatever that thing in here. Alpha particles are the most radioactive. I mean, the highest, because of their mass, they can cause a lot of problems. And beta decay is less mass than the alpha particles. But depending on, they are given a certain factor. So if you expose your skin to one or the other, of course, the beta decay will be less problematic to you because it has less mass, carries less kinetic energy than that of the alpha particles, okay? Alpha particles are actually, they go and they interact with your skin and they can cause a lot of problems. So for that, what we use the unit of REM, Röntgen equivalent men, okay? That is the measure for radiation. That is a really useful number to remember. And there is this factor in here for the dosage in order to have the equivalency in here, okay? So the factor for beta decay is 1 and the factor for alpha decay is 10. In other words, 1 alpha particle is equivalent to 10 beta particles in terms of what their health effects are, okay? Lethal dosage of radiation is 500 REM. So if you're measuring radiation, that is how much becomes lethal. And if you go and do an X-ray chest on yourself, it's not really that much exposure. It's less than 1 REM. I think it's few REMs. So it's not really this much dangerous at all. So so this is how much radiation that we have. Cosmic radiation is 33, so it's a lot less than 500 deadly cause. The ground is about 33, okay? From air is about 200 REMs, and human tissue itself, because we have potassium and calcium that we take and all of these things, they have their radioactive, it's about 35. So that's basically how much. Let's see in here an X-ray diagnostic exam. Oh, that's high, that's 40 REM, but it's not deadly. Okay, and it's very short-lived. Okay, nuclear diagnostic is about 15. From your TV, you're getting about 11 REMs. From weapon tests and fallout, so it's about 1 REM and so on and so forth. Okay. Radioactivity can be useful in technology. For example, you can check, for example, it's used in as tracers, and it's used, for example, in agriculture, trying to see how effective, for example, different what do you use for the plants to feed them? I forgot the word for it. I have the word in French, but I lost it in English. Can anybody remind me of what the word to use for the fertilizer? Okay. So to test, for example, the effectiveness of fertilizers, you put traces of radioactive materials in them and see how the plant is doing, basically. And of course, you check the material to check the radioactive material to see exactly if it's absorbing a lot of the fertilizer. Is it effective in making the plant to grow more or not, really, by using these tracers? Or also used in medicine too. For example, if you're trying to see different tissues and things like that, so what you do, you inject a person with small tracers of radioactive materials and follow them, okay, like iodine, which you use for the typhoid. Okay. Okay, again, I mentioned the fact that the only reason that we have stable nuclei is because of the fact that there are two forces competing with one another: the force of repulsion due to electrostatic force and the force of nuclear attraction. If they are close from one another, the strong nuclear force is very strong by a factor of 100. So the repulsion is there. The two protons are repelling one another. And it's strong. It's big. But it's not as strong as a nuclear attraction. So they are attracted to one another. So the two protons, if they're close enough, they will fuse actually because of this imbalance of the two forces. One of them is repelling the two because both of them are positive, and one of them is attractive, but the attraction is 130 times bigger, 137 times bigger actually. Okay. Now, if they're far away, the nuclear force is really drops dramatically. Whereas the repulsion drops also because they are far away, but not as much. So there is repulsion. So for a nucleus that is very far, where the protons are very far from one another, this force is less significant, so there is repulsion. For the nuclear, for when the nuclei are next to one another, there is attraction. So you can grow nucleus basically, and make it big and big and big up to a certain point. That's why the elements, there are 100 or so, occurring naturally about 92 elements or 90 elements in nature. And the only things we made, and they're short-lived, actually a little more than that. But the point being in here is because they make them bigger and they're totally unstable because of this thing, because of this. The next shake that you make and they're going to split up or separate. So again, that's my point in here. So the nucleons are close in here, so the force wins and they stay stable. Nucleons in here, this proton and this proton are far away and they will repel one another. Whereas this proton and this proton are close enough, so they're going to glue things. That's why you need neutrons, because neutrons, they cannot do this game. They cannot repel themselves from, or attract one another from electrostatic force. But they play the game of the nuclear force. They are actually as good as protons when it comes to nuclear attraction. That's why you need neutrons, to glue the nucleus together. Otherwise, the nucleus is not going to be stable. So the neutrons and the protons, they participate in the nuclear force. So the more you have, except that then if you have too much, then it becomes unstable too. Okay. A neutron by itself is really radioactive by itself and can split itself into two particles, proton and electron. So this is one way of doing radioactivity, is having a proton change into, a neutron change into a proton. Okay, so this is the beta decay, by having one of the neutrons become a proton. So now you increase from, let's say, for example, if you have 20 protons, now one of the neutrons became a proton, so you have 21 now. Whereas in the alpha particle decay, in this case, you have actually 4 of them will escape. Oh man, time is running out. We really need to expedite these things. Okay, the half-life, we discussed this for physics 11, basically, is how much time it takes for half the material to go radioactive. Okay, so that's basically how this is. So, for example, its half-life is 1,620 years. After twice as much, only left with a quarter. So 3/4 are gone. After 4,860 years, 1/8 is left. So, and 7/8 is gone, and so on and so forth. Okay, and that's how we use this process backward, by finding the ratio of these elements and deduce from this period how long this sample has existed. Again, we use detectors like Geiger counter millers to basically find how much radiation there is. As the radiation hits this detector, it's going to basically trigger a current, and the current will be a click actually in here, and that is going to be measured in this case. Actually, there is a voltage in here. There is a high voltage in here. Once a particle hits it, you're going to have the radiation detected. Okay, I talked about the bubble chamber, and that's basically where we discover all these traces in here of different elements. That is basically the radiation that you have. If you happen to go to a nuclear laboratory anywhere, I have had the chance to visit a couple of them. At least one, in some places they give you in the public, you can go and see the cosmic radiation that is falling in that chamber actually, and you see it live, and you see the traces different. Every time an element hits, you're going to see it there. I mentioned transmutation basically is changing an element from a different element, like uranium, for example, 238, splitting itself and becoming thorium-234, and plus a alpha particle in this case. Okay, the half-life of this one is very long. Now, thorium itself can go to palladium plus, what is it? Protactinium. Oh man, you can't say these things. Okay, I can't say them anyway. Okay, I thought it's, no, the other one is a different symbol. Plus beta particle. Okay. And I mentioned the fact that different ones in the alpha particle, the process is the number is reduced by 2. In the case of beta particles, when an element ejects an alpha particle and a beta particle, because it's going to reduce by 2 and adds 1, so it's going to be a net loss of 1. Because a beta particle will increase it by 1. I mentioned radiometric dating, basically, and how we use the process backward, using half-life as a standard. Depending on the element we're trying to find, we're going to find the life, basically, of this one, the element that we have in here. Okay, you have carbon-14 in here and nitrogen-14, and how they basically add nitrogen, and you're going to get into the this is a different radioactivity in this case. This is actually a proton. Okay, we mentioned before. Carbon-14 can decay by itself into nitrogen-14 and giving up an electron in this case. Okay, this is a beta decay. So again, we know the half-life of carbon, okay, which is 5,730 years. So if you measure how much carbon-14 versus how much carbon-12, or nitrogen in this case, you're going to find how old this, when the last basically living organism basically was alive. So if you find this much compared to how much it should be, then you know how long it was long ago when it died, basically, because it stopped producing carbon-14 at that time the minute it died. It stops making it. So whatever it has is going to go radioactive and decay until this is how much you're left with it. Okay? So brings me to the other points in here, that is the Otto Hahn was credited with the discovery of the fission, but it's actually other people who worked on it. Okay, and basically, when the element becomes too big, like uranium-235, for example, it's really unstable. So the minute it's moved away, it's going to split. And that is one way of doing it, for example, is hitting it with a neutron. Once it hits it, it's going to cause it to split into 2 different elements, plus 3 neutrons that are ready to cause 3 more uranium-235 to split. This is uranium-235 to split. So this is called a chain reaction, because once it starts with 1 can lead to 3 more. And each one of the 3 potentially can lead to 3 more. And each one of the, so basically this will lead to 3, this, so you have 9 now. And each one of the 9 can lead to 3 more, so you have 27. And each one of the 27 can lead to 3 more, 81, and so on and so forth. So the thing will grow exponentially very quickly. Okay, unless you control it, unless you put rods in here to limit how many will come out. For example, if you only will consume 2/3, then at the end, each step will lead just to 1 step more. Okay, so in that case, the nuclear reaction is controlled. That's what's going on in nuclear reactors. In a bomb, no. In a bomb, you let everything start and go exponentially quickly, and the bomb explodes in every which way. Okay, so that's basically what this idea is. And again, it depends on something called the critical mass. The critical mass is really what is needed, because if the mass is too small, then the electrons will escape the surface and you're done, because the ratio of the surface to the volume is very low for small value, for small masses, whereas it's very big in here. So there is still escaping, and the same number of neutrons escaping the surface. But at the end, you have a lot of them inside who can cause they can trigger the explosion. So there is really a critical mass that you need in order to have a bomb. Okay, the initial bomb was not really that big, at least the one that was dropped on Hiroshima. Again, fission, this is how basically the bomb is. So once you have the barrel that is started and you have a critical mass met, then you have enough for control. This is a controlled reaction. A controlled reaction is that you have rods basically that are used to control the nuclear reaction. Okay. This is a typical nuclear reactor. This is the design for it. So what you have in here, you have the fuel rods, and between them there is a control rods. Control rods, for example, they could be graphite, they could be any material that absorbs the neutrons. So if you make them all the way to the bottom, then in this case the nuclear reactor is shut down. It's not working. If you pull them a little bit, the nuclear reactor starts to work, basically starts to produce energy. So that energy is heat, and the heat is absorbed by this fluid, which is typically water. It's going to boil, and as it boils now, there is a heat exchange in here so this water is actually radioactive. It has a lot of radioactive materials in it, neutrons and other stuff in it that's produced. So you want that to be insulated. So it's pumped back into the nuclear reactor when it cools down, and after it cools down, it's going to warm up and comes into this other tank, and in here it's going to exchange the water. So it's going to heat up this water, and this water again is going to come super hot, and as it's coming super hot, it turns the turbine, and the turbine will produce, per Faraday's law, the electricity. It cools down, and there is another pump, okay, that's going to push it back into the boiler in this case. And this one also, there is another pump. So that's really how the process is. The purpose of which at the end is to turn a turbine, which is a big magnet, inside coils, using Faraday's principle to generate electricity. Whether the falling water creating the current or this one in here, that is the same thing. It's the same principle, making electricity. From this point on, it's similar to how for example, the electricity that is produced in Hoover Dam is. But from here, it's a different process. It's actually the water that comes rushing from this process in here, super hot, and it gives the heat to the cool water in here. And this one is boiled then, but then it's going to be pumped through the nuclear reactor. The nuclear reaction becomes, if you want to produce more energy, all you have to do is pull the rods up high. If you want to shut it down, you just push it down. So that's basically how the nuclear reactor is. Again, I mentioned the fact that these nuclear reactors can be producing, because the materials that is going to be produced in this reaction in here, because you have to change the fuel rods. After a while, they become basically less and less uranium-235, but more and more plutonium-239. So we're going to take them and replace them with the new fresh rods, and the rods that you have in there, plutonium-239, is really also radioactive, but it requires a different operation, different mechanism to produce energy. So it's not going to be used in this nuclear reactor. It's going to be used in a different nuclear reactor. But that's basically how the process works. So right now, what we're doing, we're burying them. I think the United States stopped doing this completely. It's called breeder reactors. Okay. Again, we produce a lot of power, and the power is based on this expression, really. That's how much energy is produced, as I mentioned before. Okay. So how do we know that? The experiments that were done on the isotopes using mass spectrometer, and mass spectrometer is nothing but a big magnetic field, basically. As different isotopes will come in, they're deflected because of the mass. Okay, so uranium-235 comes from one side, uranium-238 is much heavier and require a high radius to go through. Both of them are isotopes, both of them have the same ions, both of them have the same number of protons. They are only different in the same number of neutrons. And that's how we isolate them, and that's how we discovered the accuracy of this expression. So again, as the atomic number increases, the nuclear mass increases with it. That's typical, again, because of the stability of the atom. This is what I was talking about in here. The rock bottom is iron. Symbol for it is Fe. From this side up to here is nuclear fission. Because what you're doing in here, you're basically splitting atoms. And from this side, you're fusing them. Nuclear fusion from this side. And as you do, the products have less mass than the reactants. The difference in mass is the energy released. From this side, as you're breaking them, as you're splitting them, you're going to have products that are less mass than the reactants. The difference, again, is this energy. But as you can see, the gap in here is smaller than from this side. That's why fusion is actually far more effective if we can control it than fission. Okay? That's really, this graph explains everything. And as I mentioned before, iron is useless in terms of its nuclear reactivity. It doesn't react with anything. It's the bottom of everything, okay? It's the hole where everything goes into. And as far as stars are concerned, once they make that, that signs their death. They are not going to be really making any more. As a matter of fact, that's item 2, okay? What is so special about iron? It's the most stable in terms of the ratio of mass difference or mass per nucleon in terms of all of the elements. It has the highest, if you wish, mass per nucleon in terms of all of the elements. And also, when a star makes it, it really, the word for it is, it has signed its own death. It's going to go supernova. Okay? Yes, just refer to slide 84. Again, I explained this process for the fission. Okay, and this process for the fusion. And the difference in mass is what we know as energy because of E equal to mc squared. And this is the difference in mass in here, translated into how many mega electron volt that you're going to end up with. Okay. Confining controlling the fusion is a big problem at this point. We really don't master it. This is one way, is dropping the hydrogen basically pellets inside the laser beams, but that is still not really is not really doing it, or is using magnetic fields also. It's still something, if a civilization will control it, if a country does, they will have tremendous amounts of free energy, or at least very, very abundant energy with very little cost. At this point, it's not done. Okay, nobody could have done it. There's tremendous teams, and I know at least Dr. Maple and UCSD and other people working on this project for a long time. Until now, nobody could have really come up with a solution to it. Okay. So there were 2 questions today. I hope you guys got them. They're in the discussion if you just basically trying to go through them. And I'll see you guys on Thursday. And I'm going to stop the recording first. Okay, see you guys. See you, Kyle.